Hello everyone, and welcome to Linux Forensics here at Pentester Academy. In this video, we're going to talk a little bit about file system analysis, and in particular, we're going to start getting into the extended to file system. So as a review, we've come quite a ways. We've gone from the original call, determined that there was an incident, did some live analysis, and now we're doing dead analysis. We've acquired our images. We've begun doing a little bit of our dead analysis, and we've done a lot of first steps. And now we're getting ready to dive in to that file system. So let's talk about this extended file system. What is it? Well, it's based on the Unix file system, or UFS, and it's simpler than UFS. There were a lot of features in UFS that weren't really needed anymore, and so they got rid of those, made it simpler, and that's where we get the extended file system from. Now, it's meant to be pretty robust and also to deliver good performance. It's by far the most common Linux file system. Now, ext2 is common for partitions that don't change, and the reason for that is that it is a non-journaling file system. We'll talk later about what a journaling file system means. So for things like your root directories and your home directories, we tend to use the ext3 or ext4 file systems because those are journaling. So those are good for anything that might change frequently. So things like boot partitions, ext2 is fine. It's a little bit simpler, a little bit less overhead. And for most everything else, we use ext3 or ext4. So what does it look like? If you look at the structure of an ext2 file system, you will see that the file system is arranged in groups of blocks. So what is a block? A block is just what it sounds like, a block of data. Now, typically a block will either be 1K, 2K, or 4K. So if it's a 1K block, then you will have 2 sectors per block because in most media, a sector is 512 bytes. So we will start our file system with some boot code, and then we will have a series of block groups. And within each block group, we will have something called a superblock, which we'll discuss more later. And the superblock gives you details on the file system. So how many blocks in total are there? How big are the blocks? How many groups are there? Etc. All of that's in the superblock. The superblock is repeated in every block group. And this allows you to have some redundancy in case the main superblock in the first group goes bad. You have other things in each group. You have a group descriptor, a data block map, an inode bitmap, inode tables, and then data blocks. And we will drill down on all of these in the future. So don't be worried if some of this is foreign to you just now. So one of the reasons that I wanted to start talking about this stuff before we continued with some more things that we really can do with our mounted file system is that it's important for you to understand how this works at a certain level in order to understand why we might do certain things with a mounted file system. Very central to the ext file systems is something called an inode or index node. And an inode stores all of the metadata for a file or directory. So we have our inode that has some information, and then it has pointers, if you will, to up to 12 direct blocks and these are data blocks. So if we have a small file, just one inode is enough to point to all of the blocks that make up the file. If it's a little larger, it will have a pointer to an indirect block. So in the second block here, you will have a list of blocks. So this is if you have more than 12 blocks that make up your file, you might do this. And there's a facility for a pointer to a list of blocks that contains lists of blocks, and those point to actual data blocks. So you have the indirect and the doubly indirect. This allows you to very simply store large and small files. Next, file systems have optional features. They have 3 categories for these features. We have what we call compatible features, and if your OS doesn't support that feature, it can still safely mount the file system. It's just an extra feature. If it's an incompatible feature, if your operating system doesn't support the feature, it shouldn't mount the file system. We have compatible read-only features, and if your OS doesn't support the feature, you can still mount the file system, but only as read-only. Now, if you are investigating a suspected attacker's machine, they might have non-standard extensions. So that's something to keep in mind. We've so far been doing some incident response on a machine that we suspect someone attacked. But if you're actually looking at a attacker's Linux system, then you might want to be aware that there could be some experimental features. So what about the superblock? The superblock is 1024 bytes from the start of the file system, and it's 1024 bytes long. And what does it have in it? We said that it's repeated in each block group, and it has things like the block size, total number of blocks, how many blocks are there in each group, how many reserved blocks are there before the first block group, how many inodes are there in total, how many inodes are there per group, what's the volume name, what is the last write time for the volume, when is the last time that the volume was mounted, and where was it last mounted. There's also information that tells you if the file system is clean. Was it cleanly mounted and unmounted, etc. So how can you get some basic information for an X2, 3, or 4 file system? It's pretty easy to do, and I'm going to use a tool from the Sleuth Kit to do this. So I'm here at my command prompt, and I am going to run fsstat. Before I can run fsstat, I need to know where the partition starts. And we showed you before that you could use fdisk on a disk image. So I'm going to do fdisk on media, Phil, Toshiba, disk images 2015, 3, 9, img, and I'll run fdisk on that. Hit P to print. Here's the important part. My file system starts 2048 sectors into the file system. Now I run fsstat -o with an offset of 2048 on media, Phil, Toshiba, disk images, 2015, 3.9, img. I will get a bunch of information. I'm going to pipe this to more for now. And you'll see it starts out telling me this is an ext4 file system. Here's the volume ID. Here's when it was last written, when it was last checked, when it was last mounted, and it was unmounted properly, so it's clean, and it was mounted as a root file system. And here we have that list of features. So our compatible features are, it's a journaling file system, it has extended attributes, resizable inodes, directory index, incompatible features, file type, extents, and flexible block groups. Read-only compatible features, sparse super, large file, huge file, and extra inode size. And then we have some more metadata information. So our inodes range from 1 to 1,048,577. It's right here. I have the root directory in block 2, which is the standard. Here's how many free inodes I have. Here's the inode size in bytes, 256 bytes. So half a sector, 16 block groups per flex group. Block ranges, sizes, in this case 4K, how many free blocks. And we have 128 block groups with 8K inodes per group and 32K blocks per group. And then this tool will iterate over each of those block groups, which for our purposes here is not terribly interesting. Well, that's all for this video. As always, if you're enjoying these videos here at Pentester Academy, please tell a friend. We'll see you soon.